The co-authors of this paper have worked together for the last 10 years in various aspects of wireless measurement and wireless control. In the presentation today, I'll be first giving an introduction that gives an overview of wireless devices as they're applied in the process industry. Then I'll look at some of the technical challenges and solutions in terms of applying wireless measurement and control. And in the rest of the presentation, I'll focus on the ongoing development of wireless throttling valves, some of the technical challenges that we face in terms of doing control with wireless throttling valves, some solutions to those challenges, and then be showing some field trial results based upon a prototype wireless throttling valve. Since wireless field devices were introduced into the market in 2009, there's been a broad acceptance of these within the process industry. The physical layer of these devices are based upon the IEEE 802.15.4 standard. In most cases, the protocol and the communication stack of these devices is based upon the Wireless HART International Standard, the IEC 62591 standard. A wireless transmitter can communicate a measurement to a control system in a couple of different ways. It can be set up to communicate continuously. That means that the device periodically wakes up, communicates its value, and then goes back to sleep. The period at which it wakes up is configured by the user. As a result, you have a periodic update of the measurement going into your control system. The other technique that can be used is called window communication. The device periodically wakes up, but then rather than communicate the value, it compares the value to the last communicated value, and only if the difference exceeds a deadband does it then communicate the value. Also, if the time since the last communication has exceeded the default reporting time, then it also will report it when it wakes up. As a result of windowed communication, we have a periodic update of the measurement. This introduces some technical challenges, since most control systems today are based upon the measurement, the control measurement being periodically updated. Also, tools used in analyzing control are also based upon periodic measurement update. In most cases, the devices today are battery powered. To achieve a 5 to 7 year battery life, the fastest update rate can be 8 seconds or slower. Using the slow update rate and aperiodic communication can be a challenge. But by using the PID algorithm, it's possible to use this slow update rate and non-periodic communication quite effectively in terms of control. The PID plus is a PID in which the integral component is calculated using a positive feedback network, and the contribution due to derivative and integral are only updated when you get a new communication. The proportional action continues to operate all the time, and the actual algorithm is executed much faster than the actual communication update rate. As a result, any change in set point is immediately acted upon. The change in output introduced by the proportional action is reflected accurately then in terms of the integral calculation done with the positive feedback network. Many installations have been done in which the PID plus has been used on a variety of process applications. So this technique has been very successfully used in terms of wireless control. To give you an example of the response seen with PID plus, we have two identical processes, one controlled with PID and a wired measurement, the other with PID plus and a wireless measurement. The tuning of the PID plus and PID are identical. As we see here, when we change the set point, the control parameter response to that is almost identical for the wired versus the wireless. When we introduce an unmeasured disturbance, you'll notice the response of the wireless is a little bit poorer than the response of the wired. That's because no action is taken until a new value is communicated. But once new values are communicated, you notice that the valve position is identical to that which would be achieved using a wired transmitter with PID. So there's a little bit of difference in terms of control performance as measured by integral of absolute error, but not significantly different. The important thing here is to realize that with a wired installation you had 692 new measurements, but with wireless you only had 25. So with PID Plus it's very possible to do a very good job using the slower update rates that are required for a 5 to 7 year battery life. In some new applications such as upstream oil and gas, there's a real economic incentive to have a total wireless control loop. That is not only the wireless measurement, but also have a wireless throttling control valve. So this economic incentive is driving manufacturers then to develop wireless throttling valves. Conceptually, if you think about it, with a wireless valve, to compensate for the delay in the requested change in valve position getting down to the valve, all you would need to do is take the response to that request and bring it back into the positive feedback network rather than the controller output as is shown in this figure. By using the actual valve position in the positive feedback network, you then take into account automatically then any delay in the valve responding to the requested communication of change. In actual life, though, the problem becomes much more complicated. Most of the power associated with the actuator is used in actually moving the valve. So with a wireless actuator, there's a reason then to try to minimize the frequency with which the actuator is changed. Also, the communication from the gateway down to the valve can take some time, and also the response is not instantaneous. It can also take some time in getting back to the gateway. So we need to somehow deal with these delays due to communication. To minimize the change of movement on the valve, we can implement something called minimization of valve movement. This is pretty much like our window communication, where the PID output, changes in PID output are not acted upon unless the change in valve position from its last communicated value exceeds some deadband, or if the time since the last valve change has exceeded some default. By implementing this minimization of movement technique, then we can reduce the number of changes in valves by a significant amount. However, this doesn't help us in terms of compensating for the delay of the communication to the valve and the communication delay of the response back up to the gateway. To address that, it's been proposed that a new HART command be introduced. This command is called time to apply target output. With this new command, when a request is made to change the valve, not only the valve position is communicated, but also time to apply. So when the command is actually received by the valve, it will hold the change in position until the time to apply has been reached, and then at that time it can apply the time to apply. So for example, it might take 3 seconds to get from the gateway down to the valve, but if the time to apply was 5 seconds, it would hold the requested valve change for 2 additional seconds so that the valve changes exactly 5 seconds after the command was issued from the gateway. By implementing this time to apply, then, it's possible to calculate the valve position quite accurately, even though we can't measure it due to the delay going down to the valve and the response coming back. So if that calculated valve position then is used in the positive feedback network, we can compensate exactly for the delay introduced into the movement of the valve by communication. This shows a simulation in which the time to apply is used, and the time down to the actuator is 3 seconds, and the response time coming back is 3 seconds. As you can see, the control parameter for a set point change comes up quickly to set point. There's no oscillation, no wavering of the measurement. Very good control. The only thing you notice is that there's this time to apply delay between the change in set point and the actual process starting to change because of the valve not moving until the time to apply. In the lower graph, it shows the same kind of test where the time to the valve and the time coming back was 6 seconds. So our time to apply in that case was 6 seconds. As you see, then, the response is quite good with no oscillation, no hunting going on. And the only thing different between that and a wired installation would be this time to apply delay in the response. This shows the use of wireless valve with a wireless transmitter, in which the wireless transmitter is updated using windowed communication with a 6-second period and a 12-second default time and a 3% deadband. As you'll notice in this test, the response is quite good, no hunting, no oscillation. Responds very much like the wired installation except for the time to apply. So the response that you can achieve then with wireless valve, wireless transmitter is very much comparable to that used in a wired installation and is quite adequate for most processes within the process industry. You can do a lot of things in simulation, so we like to always test these techniques using a real process. Fortunately, Fisher Controls is a division of Emerson, and they have one of the world's largest flow labs. So using the flow lab in Marshalltown, we instrumented the Coriolis meter on the left-hand side with a wireless adapter. On the far right-hand side, you see a valve. Our prototype valve is just barely shown on the far right-hand side. Downstream of that is a throttling valve that we can adjust to introduce unmeasured disturbances into the flow process. So using this setup, we did a battery of tests of wireless control. In this test, we were looking at both the set point change and the response to unmeasured disturbances. We're looking at minimization of output change and its impact on control as well. As you'll see in this chart here, the time for a command to get from the gateway down to the valve was quite noticeable. In most cases, the command would get down within 8 seconds, and so we set the time to apply in all the tests that we did in the flow lab. The time to apply was 8 seconds. In this test, we were using a wired transmitter and wired valve. And you notice the process is quite responsive, about a 3-second process response time. There are some secondary dynamics going on due to those tanks that you noticed in the process setup. And so it's very realistic in terms of the type of noise and response that you might find in a process within a plant environment. This shows the response for unmeasured disturbance. As you'll notice, as the disturbance is introduced, the controller has to do work to bring the control parameter back to set point, and as the disturbances get bigger and bigger valve changes required to correct for the disturbance. Here we're showing the response using a wireless valve and a wired transmitter using a timed apply of 8 seconds. As you notice, the response is quite good here, almost identical to what we saw with a wired installation except for this 8-second timed apply. If we look at the response to unmeasured disturbance, again it's very similar to what we saw with a wired valve. It's a very good response to unmeasured disturbances. Here we're showing the flow lab where we're using the wireless transmitter and a wired valve. Here you notice that the response is really quite good. You do see some difference between that and what we saw with a wired installation just due to the fact that the measurement is only being updated every 8 seconds. This shows the response using the wireless transmitter to unmeasured disturbances, and again the response is very close to what you would see with a wired installation. In this chart we're showing the response to set point using a wireless transmitter updating at 8 seconds and a wireless valve with a timed apply of 8 seconds. As you can see on a set point change, the control parameter comes to set point without any hunting or oscillation. So the response is very close to what you would see with a wired installation other than the time to apply. This shows the response to unmeasured disturbances using our wireless transmitter and the wireless valve. And again, response is very good, pretty much what we saw with the wired transmitter and wired valve. As soon as we get beta adapters, we'll be testing those at the J.J. Pickle Research Center at UT. The process that we'll be instrumenting there with these wireless adapters is the divided wall column that's shown in the red here. On the column we'll be addressing on the liquid distribution 3 valves that will be the wireless adapter will be applied to. 2 of those will be controlling liquid flow. They're secondaries of a cascade, so their set point will be constantly changing to maintain level and flow ratio. The third valve will be adjusting steam to a steam heater, single loop type control where we have a constant set point in that case. Also we'll be instrumenting the side product takeoff, where we'll be doing flow control in 2 cases where the flow controller is a secondary of a cascade, and also doing our temperature control using a wireless temperature measurement as well as a wireless valve. So in the future then you can look for us to be writing a paper on the test results using the beta adapter on the valves at this particular site. In summary, it's very possible today to use wireless measurements in closed loop control. The performance is very much comparable to what you would achieve with a wired transmitter. Wireless valves are in the development stage and will be released here soon. As soon as those become available on the market, then total wireless control loop becomes possible. To implement that and provide good quality of control, then the key to that is to use this time to apply command, and also design in the modifications that we went through on the PID Plus that are required when you're dealing with a wireless valve. If you'd like more information on the work that we've been doing with wireless control, this book shown in circled in red here was released last fall. It summarizes the last 10 years of work on wireless measurement and control, and is something that we hope you'll find to be helpful. There's a website that goes with the book. On the website are YouTube videos that show the solutions to each chapter of the book, and are a good way to see and demonstrate how wireless control compares to wired control. We'd like to very much thank the different organizations that have contributed to the work on wireless control, those being Rosebunt Fisher Controls, Eastman Chemical, and UT have been very supportive in terms of the work in terms of wireless control on the divided wall column.